Welcome to this talk too. We're very pleased to welcome Capgemini team who will talk about the crucial role of AI and sustainability at Capgemini. We are going to cover three main topics, which are how to design a frugal AI, how to drive a decarbonization trajectory with data, and how to improve the energy performance of operations thanks to AI. I will now give the lead to Martin to start the presentation.
Thank you, Alexandre. Hello, everybody. I'm Martin Chauvin. I'm a senior data scientist at Capgemini Invent. And today with Hugo and Sofiane and the team around Sofiane as well, we will talk about how AI and how AI can help energy frugality and how we'll deal with this at Capgemini. So first of all, a quick word about Capgemini. Capgemini is a IT service company built around several companies, mainly Capgemini, but also Capgemini Invent, which focuses more on consulting services. Capgemini Engineering, which focuses more on the engineering processes of companies, and Sogeti and Capgemini, that focuses more on IT services. So let's start the talk. And first of all, we'll have a quick look. We'll have a look at how AI and can have an impact, and how we can eco-design algorithms to reduce the impact of AI. So first of all, what is the climate footprint of digital? So we'll start by giving you some key figures. According to several studies, ICT services account for around 4% of the worldwide CO2 emissions, and are expected to grow up to increase by 9% each year. Plus, the ICT services account nowadays for 10% of the worldwide electricity. So even though more and more services are using green electricity and carbon-free electricity, it can still have a huge impact. So in your opinion, and feel free to give answer in the chat, what percentage of the overall footprint of an iPhone does the manufacturing process account for? And feel free to answer in the chat. We'll give you a few seconds to answer and to guess, maybe. Okay, I'm not seeing many answers. Feel free to answer, and if you don't have a clue, that's all right. I can give you the answer. According to several studies, 70 to 75% of the footprint of an iPhone comes from the manufacturing part of it, which means that no matter how someone uses its iPhone, most of its footprint is already done just by buying it. Next question, maybe. Oh, chat is disabled. Oh, sorry. Well, I will give then give the answer to every question I ask. Maybe you can think about it still without answering in the chat. In your opinion, how much more energy is used when you choose to use 4G instead of Wi-Fi at home, for instance? I will give you a few seconds to think about it. Well, it could be around a 23 times increase of energy consumption. And when you're using 4G instead of Wi-Fi, that's because Wi-Fi 4G antennas are really energy intensive devices. So picture Wi-Fi when you can to decrease your footprint. And finally, in your opinion, how much CO2 was emitted to train the famous model from OpenAI called GPT-3? It's around 500 tons CO2. For reference, the Paris agreements, according to the Paris agreements, every person on Earth should aim to have a footprint around 2 tons of CO2 per year. So this is equal to a few hundred people. So now that we've seen that, we can ask ourselves, and we've seen that AI can have a huge footprint. How AI accounts in all of this, and how much we can try to improve it. So our take at Capgemini is that we should shift mindset when developing AIs to shift from an accuracy-driven mindset towards an efficiency-driven mindset. This means shifting from always looking for the most accurate AI to trying to reach the best trade-off between accuracy and efficiency. This means having the best accurate AI possible, but this also means accepting to decrease the accuracy and accepting to not go forward in development if you know that some training processes or some processes during the training will have a huge impact. Having said that, we also think that eco-design of the AI can be implemented at every step of the AI lifecycle. Thus, we've developed two assets at Capgemini that can be applied at every step of the AI lifecycle. First of all, with the asset called AI, which ensure frugality by design, and that can be applied and used during the first few steps of the AI lifecycle. Then to ensure to make sure that the design and the frugality you've designed with AI is actually implemented and deployed with your AI. We've developed Carbon AI, which allows you to monitor the energy consumption of your AI. I will now give the floor to Hugo to present you more in details about AI.
Thank you, Martin, and hello, everyone. I'm Hugo. I am a research scientist at Capgemini Engineering, and I am co-leading the research project SUSAI. So SUSAI is a research project which focuses on the assessment of the environmental impacts of an artificial intelligence solutions. So we'll present it in more details for the few minutes. Can you move? Perfect, thank you. So a few words on SUSAI. We strongly believe that it is important to assess precisely the environmental impact of your artificial intelligence solutions before its implementation, so during the conception phase. Because if you don't, you might find yourself in a place where it's difficult to reduce the impacts because they are either already done or because you don't have the tools or the knowledge to how to reduce it at such moment in its life cycle. So at Capgemini Engineering, we created a research project which gathered data scientists, PhD, data analysts, and to work on the precise assessments of an artificial intelligence solution throughout its entire life cycle. And what I want to present to you today is one key feature of our research project, which is the extensions of lifecycle assessment to artificial intelligence. And throughout this extension and throughout this work, we are able to infer guidelines and recommendations and to have a better understanding to what it takes to move towards a greener artificial intelligence. Can you move to the next slide, please, Martin? Thank you. So just a word on lifecycle assessment. It is a well-known tool to have a specific estimation, precise assessments of the environmental impacts of a product, service, a process. For example, if you take a plastic bottle, you could have, using LCA, you could have every flow, a measure of every flow coming into the bottle and leaving the bottle to the environment, from the extraction of the material to the disposal or the recycling. So, and one of the points it is that LCA is a standardized tool. So once it is developed and adaptable to your solutions, you can just follow the steps and it is really easily applicable. So it is a really interesting tool, and we want to extend it to artificial intelligence. So the first question we asked ourselves when we created the project 3 years ago, it is how to apply LCA to artificial intelligence, because it is a novel approach and few research groups are working on it. So it is quite new. And the first step was to develop a specific life cycle to define precisely the life cycle of artificial intelligence, an artificial intelligence solution, because you do not have, like, for example, raw extraction of materials or recycling, things like that. So we defined a life cycle for artificial intelligence, and in every step of the life cycle, we studied the specific flows coming into the artificial intelligence and leaving the artificial intelligence solution through to the environments to have a precise estimation of its environmental impacts. And once we have done that, we could be able to create LCA models for different case studies. And this is where it gets interesting, because once you have a precise LCA model for an artificial intelligence solution, you can have a better understanding of it. Can you move on to the next slide, please? So let's assume that I have a LCA model for specific case studies. Let's say your artificial intelligence solutions. I could have a precise measure of every impact of your artificial intelligence, its impacts on carbon emissions, minerals, water, human life, things like that. But what could be interesting is to change some parameter, to do some comparative studies. For example, what happens if I change the localization of the data center? Or what happens if I change the GPU, the CPU, the hardware, the models that I use, the deep learning models that I'm using. And what we can see, it is that small changes like this have a tremendous impact on the emissions. Just to give you a hint, In our projects, in our case study for computer vision's really simple case study, like a classical computer vision algorithm, we were able to reduce the emission impacts of our solution onto 90% of the emissions on on the different criterion impacts. So these small decisions, like these small parameters, are really important, and we use the LCA models to derive guidelines and recommendations that we want to give you and to give to the artificial intelligence communities. And this small, we will present with Martin in a few minutes some recommendation in this way. But there are some guidelines that needs to be understood, and this is an ongoing research project. So I will just now present some perspective and things that we want to work on. The first thing that we want to do is to continue in this direction and refine the LCA analysis, get a precise model, a best understanding of its flows coming and leaving it, to have a better estimation. And then we want to extend the scope to other domains, because from now on, we have mostly worked on deep learning and computer vision. And we want to extend it to different domains of deep learning, different algorithms, different models, and even different fields of artificial intelligence, because artificial intelligence is wider than just deep learning. And the third step that we feel that is interesting is the proposition of an eco score that could aggregate every aspect of an LCA analysis to give a quick understanding of how your specific artificial intelligence solution works. I hope it was clear. If you have questions, feel free to ask it by mail if you don't have the time at the end. And there are two internships that are up now for 6 months, and you can find them online and email us if you are interested. But what I want to take you away from it, one thing that we feel that is important is that eco-conception is really important, but it must be accompanied by measure. And the measurement is key in this process. Because if you only have an estimation beforehand, before the implementation, you do not have any idea of what's happening during the life cycle of the artificial intelligence, if there is fluctuation, if the estimation was good. So you want to have a measurement of the carbon emissions, which is a major contributor of the heterogeneous impact of artificial intelligence. And if you don't, you might find yourself only focusing on accuracy. And as previously said by Martin, accuracy of your model should not be the only focus, and we should shift to energy efficient artificial intelligence. So now I will give the floor to Martin to present Carbon AI.
Thank you, Hugo. Well, sorry. So yes, I will now talk about Carbon AI. Carbon AI is a tool developed at Capgemini that allows you to precisely monitor and to measure the energy consumption of any Python algorithm. So for those of you who don't know, Python is a programming language that is used in most AI projects nowadays. And so we developed this open source tool, Carbon AI, to ensure that our models we developed at Capgemini are both energy efficient and that they have a low carbon footprint. So this is a tool you can find online and open source. You can find it on GitHub. And yes, so how does this tool work? So I've made a quick video of the usage of Carbon AI. So this is a notebook, a Python notebook. So don't worry, it's just a basic tool. So for this demo, I've used a really small data set called the MNIST data set. This is a data set of handwritten digits of the pictures of it. And you have to guess the picture on the number of the picture. And then we can use our tool, Carbon AI, to monitor the energy usage of an algorithm trained on this dataset. So we've defined a really basic machine learning pipeline where we load the dataset, train the model, and test it. And then we can use Carbon AI with our power meter to monitor the training process of this algorithm. So this is a really transparent process, which means that the monitoring part runs in the background while the algorithm is trained. While when your training is done, every measure done by the Carbon AI is logged in a CSV file where you can find everything that we measured and that you declared as a user. So you can find the energy usage, the carbon footprint of the algorithm, and some other contextual information that you provided when training the algorithm. So who is this tool for? This tool addresses two teams in particular, mostly the data scientists, where they are able to get the exact breakdown of the carbon emission, which means that they are able to deep dive in their pipeline processes and the AI processes to get a better understanding at which part of the overall process has the greater impact and how they can reduce it. Because when you know which part of your pipeline is the most energy intensive, it's therefore easier to spot and to find ways to improve. Carbon AI also allows to find the optimal algorithms between that optimizes the trade-off between energy, between accuracy and efficiency, because on there you will have tools to monitor the accuracy of your algorithm, and with Carbon AI you now have tools to monitor the energy efficiency of your AI algorithm. Finally, for data science teams, Carbon AI allows to adopt better AI eco-design principles that you can measure and then you can follow in the overall building process and your AI lifecycle. For business teams, Carbon AI allows to have a precise measure and a precise breakdown of the footprint of each project that they monitor and then they are able to implement. It allows them to have an innovative carbon footprint KPI related to AI, and that allows them to integrate it in their ESG report, for instance. And finally, it also allows them to shift from return on investment to return on environment and to add it to the decision criterions. So in the data science teams, you are shifting from accurate-driven mindset to efficient-driven mindset. And you can do the same in the business when you shift from return on investment mindset to also improving the environmental impact with your project. So what's next for you with Carbon AI? Or how can you contribute? So as I've already said, Carbon AI is an open source package that can be downloaded by anybody. It is publicly available on GitHub, and I will share the link in the chat if you want to have a look. You can install it like any other Python package, and you can start to use it in your projects. And you can help us develop and improve this tool by solving open issues on GitHub. Thank you for your attention on this part. But now that you've seen that, what are some really example levers that you can implement in your daily life as a data scientist or in a data science team or business AI related to reduce your impact? So we will present you two of them. The first one is the optimization of the accuracy efficiency trade-off. And this is an example of a specific algorithm that optimizes this trade-off because it's called knowledge distillation. And what does knowledge distillation do is that you have a really big algorithm that is really accurate, but is not really efficient. And you ask this algorithm to teach to a more efficient algorithm to have the same predictions. And this algorithm is able to reproduce the same prediction as the teacher, but being really much more efficient. So for instance, Distilbert, which is the distillation algorithm from BERT, has 2/3 of the teacher parameters, and is also 2/3 time to 60% more efficient, while it retains 95% of the overall accuracy, which means that it is a great improvement when you are going to move from building phase to run phase for your algorithm, because you will put in production an AI algorithm that has a lower impact. Hugo, do you want to present this part?
Second example levels that we want to give you, it is, I was talking earlier about small parameters change that has big impacts in the consumption of your artificial intelligence solutions, of your algorithms. And obviously the localization of the data centers that you use for calculation, training, even test and design is really important because not every country has the same energy mix, and some of them are really more reliant on fuels and carbon emissions. And even if you choose wisely the country, not every data centers has the same efficiency when it comes to power usage. So there is a really informed choice that should be made there. And we want to, in the efforts that we are presenting to you today, give you the hints that localization of the data center is key. And this choice has not necessarily has to be made onto money, because as shown in this little table, for similar price, some data centers doesn't have the same efficiency and the same carbon emissions at all. And so what we want to get away from it is that data center localization is really important, and we want to find and to promote information of the efficiency and the energy mix. Thank you, Martin. Thank you, everyone, and you can take it, Martin.
Now that you've seen how we can, at Capgemini, how we eco-design algorithm using green AI principles, I will now give the floor to Sofiane to present you a real use case he led on how to reduce the energy consumption of industry furnaces.
Thank you, Martin. Hi, everyone. So I'm Sofiane Schaack. I'm a manager here at Capgemini Invent. So as Martin introduced, we addressed one use case concerning the energy sobriety for one of our clients, which is a large French manufacturing group which produce high technology value goods, so high-tech materials from different production sites involving high consuming assets like furnace or cooling arch. So here you can see one schema describing this production line involving the common to the final product. And you can see that we are driving the composition, we are making fusion, molding, and then a cooling system so that we can have the final product. So this production line involves, as I said, high consuming assets. And it has a big impact in the consumption of the industrial processes here for this client, because it represents at least about 200 gigawatt hour, and the equivalent in euros, it's about 20 millions. Today, while as you know, the energy is quite rising these days. And as we have seen with the client, this consumption is higher than the target, which has been benchmarked through the processes that they have tested. Secondly, we observed variability in the industrial processes, which can link to suboptimal consumption in energy, but also in the quality of a product, the final product created. And finally, there is a multiplicity factor, because this production line that we presented here it concerns different sites of this client. And obviously, each energy reduction we can make on one site, we can apply it also to the other ones, because the production processes are quite similar. So let me change the slide. Yeah, thank you. So how did we tackle this challenge? Through different approaches. First, they had data mastery, data governance issued, and we had to gather all the sources of data, as we will describe later on. And we need also to map all the necessary available data source in an unified view. And the approach we took here was the one of the ontology and the digital twin. The idea here is to standardize the data representation, but also define a digital twin in order to monitor, but also to simulate the behavior of a furnace and the production line in general. Finally, we use data science in order to statistically analyze the production and energy consumption, and also the viability of the processes. And also we try to bring out a new optimization lever from the viability we saw on the processes. So can you switch just before? Thank you. So first of all, just a second. First of all, concerning the energy consumption, we had reliable but simple approach here to estimate some quick win that we can have concerning the energy consumption. So what we did first was to audit the process in order to identify the suboptimal regimes compared to the benchmark that we had access to concerning these production lines. Concretely, this means to analyze statistically, but also with the business, and through iteration with the business to identify the optimization lever and see what statistically can influence the consumption, the energy consumption. Secondly, we train a machine learning model to predict the energy consumption based on different parameters that are flexible and accessible through the process. It can be a mixed card, the composition, the chemistry, the duration of the fusion, etc., etc. And once this model is trained and evaluated and is reliable, we can simulate the optimal process just by varying slightly the revealed optimization lever and compute first the likely gain in production, both in terms of energy consumption, but also in terms of quality, because we don't want to affect the production quality if we decrease the energy consumed. Thank you. So we use a second approach, mostly based on the model explainability this time. So this approach is based on another machine learning model, which is also trained to predict the casting and arch energy consumption. But this time, what we will do is to estimate the operational parameters that can impact and the way, the mechanism behind that can impact the energy consumption. So we take advantage of different explainability models. You can see here Shapley values. And thanks to this kind of model, we revealed some levers. And we had a cycle to define which levers can be important. And to do so, we propose this optimization lever to the business. And thanks to their expertise, we select the one that can be the more impactful. Finally, we perform ground tests to confirm if these levers have an operational impact in the real world, and estimate the likely gains that we can have by applying these rules to the other sites also. Can you? Yes, thank you. So there was another challenge, the one of the multiplicity of the sites and of the production lines. So as you can see from the production line that we described before, there is different stages in this production line, and at each stage, there is different data sources. This can be either from IoT sensors, but also from written reports of the operation. And we needed to gather all these sources in a standardized formulation. So we take advantage of what we call the ontology to standardize the data sources, but also the objects that will emerge from these data sources. And the other constraint that we had to deal with is also that the different production lines involve also different facilities and different productions that we need also to take into account. So there is, what is a twin in this area? So the twin in this scenario is to define the way that we will be able to standardize the data sources first, but also to replicate the different parts of a production line, so that we'll have standardized view of this production line that we will be able to replicate on the other sites. No, just go back, please, Martin, sorry. So this virtualization will lead to different advantages. The first one is data governance. We have now an unified approach to represent this data and to ensure replicability on the sites. We will be able to simulate, thanks to the digital twin, simulate the production line in different contexts, and also to optimize them and monitor the performances. And finally, we will be able to make some recommendation for the operation to optimize the processes in terms of mix card, in terms of duration of fusion, etc., to first ensure the quality of the final product, but also to try to decrease the amount of energy required to produce this final product. Yeah, you can. Thank you. So as a result, we obtain and validate 5 optimization levers, which when combined represent an amount of about 15% of energy consumption reduction, which is huge, because we also have to multiply this 15% in each site. It can be replicable in each site, which represent 20 sites, if I remember right. All of this optimization have been statistically verified, and we performed field tests to check this optimization levels. Sorry, and finally, we have been able also to address the impact of scalability and industrialization, thanks to the ontology and the digital twin approach. So yeah, I think we finished. If you have questions, do not hesitate to ask.
Yes, feel free to ask your questions in the Q&A section in the chat. Yeah, so there was a previous answer question about how to calculate the efficiency of a cloud region. So as mentioned by Hugo previously on the map, there are one key factor to take into account when choosing your server location is the energy of efficiency of and the energy mix of the country your server is located in. So for instance, if you're picking a server in South Africa or in Asia, in India, most you will have a bigger footprint because the energy mix there is quite carbon intensive. But you can also have a look at what we call the PUE factor, which is a factor that translates the energy, the cooling efficiency of the server location you've chosen. For instance, GCP, so Google Cloud provider, allows you to monitor the PUE of their server locations. So you can have also a look at this part. It can vary a lot, from 10% of the energy used from the computation to around 60% due to cooling regarding the computation energy used.
So there is a question about the variation of server efficiency during day, night, climate conditions, things like that. From what I know, yes, of course, there are variation, and we are taking interest into means of power efficiency usage, because we do not, you may want to monitor it day by day. I do not know if solution cloud providers provides this option, but power efficiency usage are average, and you can find sources where this information are available by trimester.
Yeah,
so,
you can also check online. There's a real-time data map on energy mix in Europe. I think it's called the electricity map, where you can find the real-time energy mix of a country.
And there is an initiative called Cloud Carbon Footprints, which is aiming to measure and analyze the carbon footprint of cloud services. And there are a lot of information there about PUE, power usage efficiency, GPU, CPU, things like that. So you might find answers for your specific requirements if you want specific data about cloud providers. I will give you the link in a moment.
Okay. Are there more questions? Sofiane, this is a question for you. Asking about ontology ontology and what it means exactly in operational terms.
Yes. I think to handle well the concept of ontology, just imagine that the knowledge that an operator can have regarding the process and the way that every task is sequenced and is executed by the different assets need to be digitalized, and this work of digitalizing the knowledge, the business knowledge, is called a twin. In the same way, having the data from sensors into the different platforms to work with, modeling this all, let's say, track that the data is following within contextual information in terms of units, in terms of expectations, range, variation range, etc., need to be standardized and let's say modelized in some graph view, which is also a twin in a certain sense. And all these knowledge are combined together to make possible the simulation we are seeing here, and also the monitoring of the system as it is in the real world in quasi real time. I don't know if it's clear.
Thank you, Sofiane. Yes, it's clear. There was another question from Malik regarding asking if it is possible to apply the approach described, I think with Carbon AI or with SSI independently of the cloud. So yes, Carbon AI can be used on any devices, on any computer devices, which means that you can use on your laptop or also on on-premises servers and also on the cloud servers, independently of the cloud provider. Basically, Carbon AI connects to the hardware of the machine and tries to and measures the energy consumption of the hardware while your algorithm is running, which means that it's nearly independent of your device, the device you use, as long as you have a CPU and a GPU, maybe, and RAM, etc. Okay, I don't see more questions. Feel free to ask any question regarding the presentation. Usage difference. Oh, okay. There's a question asking if Carbon AI can actually model the power usage of different approaches beforehand, if I understand the question right. So Carbon AI is more a monitoring tool, so that it will, in the sense that it will allow you to measure and to confirm your suspicions on the efficiency of an algorithm. So you will be able to quantify how much an improvement an algorithm is against another one. But I believe if you want to have an estimation beforehand, maybe SysAI is the tool more adapted to do it because they have performed an extensive research on this spot, right, Hugo?
Yes. Yes, if you want to have such information with SysAI and with life cycle assessment, it is possible. The key points of this research project is the precision of the LCA models, the modelization of your specific artificial intelligence solutions. So you can go to a level of precision taking into account quantization, pruning, things like that. So clearly, beforehand, we can have informations on this kind of features, but we have to make we will have to include it into the modelization.
Thank you. Are there more questions? How do you evaluate the performance of carbon AI? How do you know you are getting the correct figure from carbon emissions? So with carbon AI, we are leveraging some tools developed by hardware manufacturers such as Intel and NVIDIA. And we are using their tool to we are querying their tool to monitor the energy usage of the computer and the device. But I mean, we are basing our confidence in the figures on their confidence on their figures and on their tool. So I guess that's quite an assumption we are making, but I guess it's also, I mean, they're the best ones to know how their devices work. And how do we know that we are getting the correct figure for carbon emissions? Well, we don't know for sure. We are actually making an estimation based on the energy usage of the device. So to make it clear, with Carbon AI, you can measure the energy usage of your device. Then you can have an estimation of the footprint, the carbon footprint associated with this energy usage based on the PUE, the cooling factor, and also the energy mix of the country you are based in. But this is not the actual carbon emissions. I mean, I'm not sure anybody knows the real-time carbon emissions of anything. I hope I answered your question. Great. If there are not any other question, it's 7 o'clock. We are right on time. Thank you all for your attention and for your questions. Feel free to contact the team if you have more questions on any project that we've presented today. And yes, we hope to talk to you soon.
Yes, thank you very much for your presentation. We had lots of insight. I'm sure the students were very delighted to have all this information. And yes, as Martin said, don't hesitate if you have further questions to contact us. We'll be pleased to answer all of them. So thank you very much and have a good night. Cheers.
Thank you very much.
Thank you all. Bye.
Bye.